Did you know space holds secrets your textbooks never told you? That's right beyond those tidy diagrams of planets and the basic facts about gravity. The cosmos is packed with mysteries so wild, so utterly mind-bending, they'd make even the most seasoned astronomer pause in awe. Think about it. We've sent probes to distant worlds, captured images of black holes, and yet, somehow, the universe still manages to surprise us with discoveries that defy logic and stretch our understanding of reality. Today, we're diving deep into the cosmic unknown to uncover 30 space facts so astonishing, you'll wonder why they weren't part of your science class. Picture this, a place where diamonds rain from the sky, where stars scream in silence, and where time itself warps like a rubber band. These aren't scenes from a sci-fi movie, they're real phenomena happening right now, light years away. From rogue planets drifting through the void to galaxies that shouldn't exist, the universe is far stranger than we've been led to believe, and yet so much of what's out there remains hidden, tucked away in research papers or dismissed as too bizarre for casual conversation. Well, buckle up because we're about to change that. This journey isn't just about fun trivia, it's a reminder of how little we truly know. Every discovery, no matter how small, peels back another layer of the cosmic onion, revealing just how much more there is to explore. Whether you're a casual stargazer or someone who's always dreamed of touching the stars, these facts will reignite your sense of wonder. So, let's leave the textbook version of space behind and venture into the extraordinary. By the time we're done, you'll never look at the night sky the same way again. Ready? Let's begin. Right now, as you look up at the night sky, our moon is quietly slipping away, not in some dramatic exit, but at a rate so steady you'd never notice. Every single year, the moon drifts nearly 4 centimeters farther from Earth. That might sound minuscule, but over cosmic time, it adds up to something revolutionary. The reason: tides. Earth's oceans bulge toward the moon's gravity, and as our planet rotates faster than the moon orbits, those tidal bulges tug the moon forward like an invisible leash, giving it a tiny energy boost that pushes it into a wider orbit. Here's where it gets wild. This gentle cosmic dance has consequences. In about 600 million years, the moon will be so distant that total solar eclipses, those breathtaking moments when the moon perfectly blocks the sun, will vanish forever. The moon's apparent size in our sky will shrink, leaving it too small to fully cover the sun. But that's not all. As the moon retreats, Earth's rotation slows down, stretching our days longer. Billions of years from now, a single day could last over a month by today's standards. Imagine waking up to a sunrise that lasts for weeks, and tides. They'll weaken, reshaping coastlines and marine ecosystems in ways we can barely predict. This isn't just some distant hypothetical, it's a slow-motion transformation already in progress. The moon's retreat is a reminder that even the most familiar parts of our universe are in constant, imperceptible flux. So next time you gaze at that glowing orb in the sky, remember, it's not just a silent companion. It's a traveler inching away 1 centimeter at a time, rewriting Earth's future with every passing year. While most planets spin gracefully like tops as they orbit the sun, Venus does the cosmic equivalent of walking backward through a revolving door. It's the solar system's ultimate rebel, rotating clockwise while nearly every other planet, including Earth, spins counterclockwise. Picture a celestial ballet where one dancer suddenly decides to moonwalk while everyone else twirls the opposite way. But Venus doesn't stop there. Its rotation is achingly slow, taking 243 Earth days to complete a single spin. That's longer than its entire year, which zips by in just 225 days. On Venus, a sunrise to sunrise lasts longer than a trip around the sun. So how did this planetary oddball end up spinning backward? One leading theory suggests a cataclysmic collision billions of years ago, when a massive object, perhaps a protoplanet, slammed into Venus with enough force to flip its rotation or bring it to a near standstill before it began spinning the wrong way. Others propose gravitational tugs from the Sun's intense pull or interactions with its dense atmosphere over eons. Whatever the cause, the result is a world where the Sun rises in the west and sets in the east, hidden beneath thick clouds of sulfuric acid that swirl at hurricane speeds. Those clouds aren't just a veil, they're a thermal blanket, trapping heat so effectively that surface temperatures could melt lead. Here's the irony: while Venus' backward spin makes it unique, its thick atmosphere means you'd never see it from the surface. The sky is a perpetual, hazy twilight, with no clear view of the Sun's bizarre path. It's a reminder that even the most glaring anomalies in space can remain hidden, waiting for probes and radar to reveal them. Venus doesn't just challenge our expectations, it obliterates them, proving the universe has a flair for dramatic contradictions. High above Saturn's North Pole, a geometric wonder defies everything we know about planetary weather, a perfect hexagon wider than two Earths, with each side stretching nearly 30,000 kilometers. This isn't some trick of light or camera artifact. It's a colossal, six-sided storm raging in the gas giant's upper atmosphere, first spotted by Voyager in the 1980s and later confirmed by Cassini. Think about that, a hurricane so precise it looks like it was drawn with a cosmic protractor, spinning for decades without losing its shape. What makes this hexagon even stranger? Its walls are sheer cliffs of wind, screaming at speeds over 300 kilometers per hour, yet the structure itself rotates in sync with Saturn's deep interior, almost as if anchored to the planet's core. Most storms, even Jupiter's great red spot, churn in chaotic swirls, but it's a polygon of pure order, a shape you'd expect in a honeycomb, not a hydrogen-helium atmosphere. Scientists are baffled. Some think it's the work of standing atmospheric waves, like vibrations in a flute, forcing the jet stream into this angular path. Others point to vortex dynamics, where smaller storms cluster and sculpt the flow into sharp edges. There's even speculation about deep-seated convection currents rising in hexagonal patterns, imprinting their geometry on the clouds above. And here's the kicker. Below the hexagon, Saturn's North Pole hides another surprise, a swirling cyclone perfectly centered within the hexagon's boundaries, like the pupil of a planet-sized eye. The hexagon isn't just a curiosity, it's a portal to understanding how fluid dynamics operate under conditions we can't replicate on Earth. No lab can simulate winds that fast, pressures that extreme, or scales that vast. Every time we look, Saturn whispers a reminder: the universe doesn't play by our textbooks, it invents its own rules, then dares us to figure them out. If you think Mercury is just a blistering wasteland where nothing could possibly survive, think again. This tiny planet, where daytime temperatures soar hot enough to melt lead, hides a secret in its polar shadows, vast deposits of ice. Yes, ice, on a world where the sun's glare is 11 times brighter than on Earth. Frozen water lingers in deep, sunless craters near the poles. These aren't just tiny patches either. Radar signals bouncing back from Mercury's surface reveal enough ice to bury a city several meters deep. How does ice exist on a planet that practically sits in a cosmic furnace? The answer lies in Mercury's extreme tilt, or rather, its lack of one. Unlike Earth, which wobbles on its axis, Mercury stands nearly straight up, leaving its poles in near-permanent shadow. Inside some craters, sunlight hasn't touched the ground for billions of years. Temperatures there plunge below negative 170 degrees Celsius, creating natural freezers colder than Antarctica's deepest ice. And the ice itself, it likely arrived via comet impacts, with frozen water crashing onto the surface and settling in these eternal shade zones, sheltered from the sun's relentless heat. But here's the twist: Mercury's ice isn't pure. Mixed with dark, organic compounds, it looks more like a dirty snowbank than pristine glacial sheets. Some scientists speculate these organics might be the same carbon-rich materials that seeded life on Earth, delivered by the same icy wanderers. The discovery reshapes how we see the solar system's inner realms, proving even the harshest environments can harbor secrets. Imagine standing at the rim of one of these craters. Beneath your feet, just a few steps into the abyss, the ground would shift from scorching rock to frozen wilderness. Sunlight never reaches these depths, preserving a pocket of ancient ice in a world otherwise defined by fire. It's a paradox that challenges our assumptions about where life's ingredients can survive. Mercury's ice isn't just a scientific curiosity, it's a clue, hinting that the universe stashes its treasures in the unlikeliest of places. Jupiter's great red spot isn't just a storm, it's a solar system icon, a swirling tempest so vast it could swallow Earth whole. But this ancient maelstrom, observed since the 1600s, is quietly undergoing a cosmic identity crisis. For over 400 years, astronomers have tracked its crimson whirl, watching as what was once a gaping wound in Jupiter's atmosphere has begun stitching itself shut. In the late 1800s, the storm spanned over 40,000 kilometers, wide enough to fit 3 Earths side by side. Today, it's barely half that size, shrinking faster than ever. The numbers tell a sobering story. By the 1970s, spacecraft like Voyager revealed the spot had narrowed to 23,000 kilometers. By 2014, it was down to 16,500. Now, it's still wider than our planet, but barely, and the rate of shrinkage is accelerating. Some researchers warn it could vanish entirely within our lifetimes, collapsing into a memory as fleeting as Jupiter's fleeting clouds. What's strangest isn't just the shrinkage, it's how the storm is changing shape. Once a proud oval, the spot now looks more like a crumpled paper ball, its edges fraying as smaller storms buffet its sides. Yet despite the chaos, its wind speeds remain fierce, exceeding 600 kilometers per hour. That's the puzzle. The storm isn't weakening, just compacting, like a boxer tightening their guard. So why is this centuries-old behemoth fading? Some blame Jupiter's churning interior, where energy shifts may be starving the storm of its fuel. Others point to interactions with neighboring jet streams, which could be stealing its momentum. There's even speculation that the spot's own turbulence is cannibalizing itself, its outer bands dissolving into the chaos. But here's the twist: the great red spot might not be dying, it might be evolving. Storms on Jupiter don't follow Earth's rules. Down there, cyclones merge, split, and reignite like phoenixes. The spot could simply be entering a new phase, shedding mass until it stabilizes. Or maybe it's feeding fresh vortices that will one day birth a successor. Either way, its slow disappearance is a rare chance to watch planetary weather rewrite itself in real time. Every telescope pointed at Jupiter isn't just observing a storm, it's witnessing a cosmic clock ticking down toward a moment no human has ever seen. The day the solar system's most famous storm finally blinks out. Astronauts returning from spacewalks often report something bizarre: the unmistakable scent of seared steak clinging to their suits. Not the fresh, crisp aroma of the cosmos you might expect, but something closer to an overcooked barbecue. This isn't space madness, it's science. The moment they crack open the airlock, veterans describe a metallic, charred odor, like burnt metal mixed with welding fumes or a sizzling skillet. Some even compare it to hot gunpowder or a car's engine after a long drive. So where does this cosmic barbecue smell come from? Blame it on polycyclic aromatic hydrocarbons, complex molecules floating in the void, born from dying stars. These carbon-rich compounds cling to astronaut suits during spacewalks, and when they re-enter the pressurized cabin, the oxygen reacts with these residues, creating that distinct seared meat scent. Think of it like the universe's version of a grill, only instead of flames, it's the chemical aftermath of stellar explosions you're smelling. But here's the kicker: space itself has no smell. Without air to carry scent molecules, you wouldn't detect a thing out there. The aroma only materializes when those star-born compounds hitch a ride back inside, mingling with the station's atmosphere. It's a fleeting reminder that space isn't empty, it's a soup of elements forged in stellar furnaces, and sometimes they leave their mark in the strangest ways. What makes this even wilder, not all astronauts agree on the exact scent. Some swear it's more like raspberries or rum, thanks to other organic molecules like ethyl formate, a compound that, ironically, gives raspberries their sweet scent and rum its boozy kick. Imagine floating in the void, surrounded by the ghostly sweetness of cosmic candy, only for it to morph into a steakhouse aroma upon re-entry. The universe has a sense of humor and a very peculiar perfume. Next time you look up at the stars, remember, the final frontier doesn't just dazzle the eyes. If you could take a deep breath out there, you might catch a whiff of something bizarrely familiar, like the aftermath of a backyard cook-off, courtesy of the cosmos itself. Imagine crushing the entire mass of our sun into a sphere smaller than Manhattan. That's the mind-numbing reality of a neutron star. These cosmic leftovers, born when massive stars collapse in supernova explosions, don't just defy logic, they rewrite it. Take their spin, for instance. While Earth lazily completes one rotation every 24 hours, a newborn neutron star can whirl up to 700 times per second. That's faster than a blender's blades, with the energy to fling material into space at nearly the speed of light. How does something so dense spin so fast? It's all about conservation, specifically angular momentum. Picture an ice skater pulling their arms in to spin faster. When a dying star collapses, its core shrinks from millions of kilometers to mere kilometers, amplifying its rotation like a cosmic top winding tighter and tighter. The result, a pulsar, a neutron star with beams of radiation shooting from its poles like a lighthouse. Every time those beams sweep across Earth, telescopes detect rhythmic pulses, sometimes with precision rivaling atomic clocks. But here's where it gets surreal. That sugar cube-sized chunk of neutron star material, it would weigh about 1 billion tons on Earth, compressed so tightly that protons and electrons merge into neutrons. The star's surface is a crystalline crust harder than diamond, floating atop a superfluid core where particles move without friction, and those lighthouse beams. They're not just light, they're concentrated radio waves, X-rays or gamma rays, powered by magnetic fields trillions of times stronger than Earth's. Yet even these spinning monsters slow down. Over millennia, their radiation beams sap energy, gradually reducing their RPM. The fastest known pulsar, PSRJ 1748-2446 AD, still clocks in at an eye-watering 716 rotations per second, fast enough to stretch its equator at a quarter the speed of light. If you stood on its surface, which you couldn't because you'd instantly be crushed into a quark soup, time would warp dramatically. A single minute there could feel like years back on Earth, thanks to Einstein's general relativity. What's truly humbling is how these cosmic powerhouses serve as universal laboratories. Their extreme conditions let physicists test theories of gravity, nuclear matter, and quantum mechanics in ways no Earth-bound experiment could. Some pulsars even orbit other neutron stars, spiraling together in a dance that emits gravitational waves, ripples in space-time first predicted by Einstein. Every pulse from these stars isn't just a beacon, it's a telegram from the edge of physics, reminding us that the universe's wildest inventions are also its most revealing. To grasp the sheer enormity of our sun, picture this. Its core alone could swallow over 1.3 million Earths whole, not just stacked side by side, but packed into that searing, nuclear-powered heart where temperatures soar beyond 15 million degrees Celsius. That's hotter than anything humanity could ever recreate, a furnace so intense. It forces hydrogen atoms to abandon their identities, fusing into helium under pressures unimaginable on our tiny planet. Let's break that down with a thought experiment. Imagine Earth shrunk to the size of a marble. Now picture a stadium, not just any stadium, but one built to hold millions. The Sun's core would be that colossal arena, its seats filled with marbles representing our planet, stacked floor to ceiling. Every second inside that stadium, an unfathomable 4 million tons of matter transforms into pure energy. That's the weight of 8 great pyramids of Giza vanishing into light and heat in the blink of an eye. But here's what defies intuition. Despite this staggering scale, the Sun's core is denser than lead. Atoms there aren't neatly spaced like in a gas. They're squeezed shoulder to shoulder, packed tighter than commuters in a rush-hour subway. The gravity crushing inward is so relentless that protons, which normally repel each other, are slammed together with enough force to overcome their mutual hatred, a process called quantum tunneling. Without it, stars wouldn't shine and life wouldn't exist. And yet, for all that density, the Sun's core is just a fraction of its total volume, barely 1%. The rest is a churning plasma ocean where energy takes hundreds of thousands of years to bubble up to the surface. If you could stand at the core's edge and survive the instant vaporization, the light you'd see generated wouldn't reach the surface for millennia. That photon bouncing toward you, it might have been born when early humans first tamed fire. This isn't just about big numbers. The Sun's scale reshapes how we see our place in the cosmos. Every drop of water, every breath of air on Earth owes its existence to that distant nuclear crucible. Even from 8 light minutes away, its gravity holds us in an unbreakable embrace, dictating our orbit with the precision of a cosmic metronome. The next time you feel sunlight on your skin, remember, you're being touched by energy forged in a place so vast, so violent, it defies human scales. A furnace where the universe itself learned how to build worlds. While Earth's sunsets paint the sky in fiery oranges and deep reds, Mars serves up something straight out of a sci-fi dream, a sunset bathed in cool, ethereal blue. Picture this: the sun dips below the Martian horizon, casting long shadows across rust-colored plains. But instead of the warm glow we're used to, the sky takes on a hazy cerulean hue, like twilight filtered through frosted glass. This isn't artistic license, it's science in action, and NASA Curiosity rover has captured it in stunning time lapses that look more like surreal art than planetary reality. So why does Mars flip the script on sunsets? It all comes down to dust, fine, powdery dust that hangs perpetually in the thin Martian atmosphere. On Earth, our thick air scatters shorter blue wavelengths of sunlight, leaving the longer red and orange ones to dominate at sunset. But Mars' atmosphere is just 1% as dense as ours, and those tiny dust particles are perfectly sized to scatter blue light instead. When the sun sits low, its light travels through more of this dusty haze, amplifying the effect. The result, a twilight palette that would leave Terran poets speechless, a soft blue halo clinging to the sun, fading into a pinkish band higher in the sky. Here's what makes it even stranger: the color shifts depending on where you stand. Curiosity's footage shows the blue intensifying right around the sun, while the rest of the sky glows a muted copper, a stark contrast to Earth's uniform wash of color. And because Martian dust storms can swell to engulf the entire planet, the intensity of these blue sunsets varies with the seasons, growing more vivid when dust levels peak. But the real magic lies in the details. Sunsets on Mars unfold in slow motion, thanks to the planet's longer day. From first glow to last light, the show lasts nearly twice as long as Earth's, giving rovers and future astronauts front row seats to a daily spectacle that never gets old. Imagine sipping Martian coffee, if coffee existed there, inside a habitat, watching that blue glow stretch across the horizon, knowing you're witnessing something no human eyes saw up close until this century. This isn't just a cosmic curiosity, it's a lesson in atmospherics. Every sunset in the solar system is a fingerprint, revealing the unique makeup of a world's air and dust. Venus' sulfuric acid clouds would bend sunlight into eerie, diffused shadows. Titan's methane-rich skies might cast a dim orange pall over Saturn's rings. But Mars, it offers a quiet reminder that even the most barren landscapes can harbor moments of surreal beauty, painted in colors we never expected. So next time you watch the sun sink below Earth's horizon, spare a thought for that little blue sunset unfolding simultaneously on Mars, a silent, dazzling encore to the day's cosmic performance. Venus is the ultimate cosmic paradox, a planet where time itself seems to have gotten twisted. While Earth completes a full spin in 24 hours, Venus takes a leisurely 243 Earth days just to rotate once. That means if you stood on its scorching surface, you'd witness a sunrise so slow, it would take over 4 months of Earth time just to see the sun crawl from horizon to horizon. But here's what really bends the mind: Venus' entire trip around the sun, its year, is only 225 days. That's right, a single day on Venus actually outlasts its entire year. Imagine throwing a birthday party there. You'd blow out the candles, celebrate for months, and by the time the party finally ended, your year of existence would have already come and gone. It's like living in a time warp where calendars make no sense. And if that weren't strange enough, remember Venus spins backward compared to nearly every other planet. So while you're waiting half an Earth year for the sun to rise, it wouldn't even come up in the east. It would creep up in the west, lingering in the sky like a slow-motion specter before dipping back down in the opposite direction. Why does Venus drag its feet so much? Scientists suspect a violent past, perhaps a titanic collision early in its history that slammed the brakes on its rotation, or the gravitational tug of war between its thick, suffocating atmosphere and the sun's pull. That atmosphere isn't just heavy, it moves faster than the planet itself, whipping around in hurricane-force winds that might be stealing momentum from the surface below. Whatever the cause, Venus stands as a cosmic oddity, proving that even the simplest things like days and years don't always follow the rules we're used to. It's a humbling reminder that the universe doesn't care about human rhythms. While we're down here counting seconds and seasons, Venus operates on its own bizarre clock, spinning lazily under a sky where time itself feels stretched thin. The next time you complain about a long day, just remember, on Venus the day never seems to end. Somewhere in the constellation Cancer, 40 light years from Earth, a world shimmers with a brilliance that would make a jeweler weep, a planet literally made of diamond. Meet 55 Cancri, a super-Earth twice our planet's size but 8 times as massive, orbiting so close to its star that a single year lasts just 18 hours. Under that crushing gravity and scorching heat, carbon, the same stuff in your pencil lead, has crystallized into a vast planetary diamond. Forget mining expeditions, though. This glittering gem's surface temperatures hover around 2,700 degrees Celsius, hot enough to liquefy steel and vaporize any spacecraft daring enough to land. But here's the twist: 55 Cancri isn't just a solid diamond orb. Scientists suspect it's layered with a diamond-rich crust encasing a heart of graphite and even liquid carbon deeper down. Imagine mountains of diamond towering over lakes of molten graphite with skies choked by carbon-based vapors. If you could stand on its surface, which you couldn't because you'd be simultaneously crushed, melted, and asphyxiated, the ground beneath your feet might crack like a colossal diamond sheet, revealing rivers of tar like carbon compounds. The numbers are staggering. Based on its estimated composition, this planet's diamond content could be worth $27 nonillion. That's 27 followed by 30 zeros. To put that in perspective, it's more money than exists in all of Earth's economies combined, multiplied by 1 trillion. But here's the cosmic punchline. Even if we could mine it, flooding the market with that much diamond would instantly render the gemstone as worthless as sand. What makes 55 Cancri even more fascinating is how it challenges our ideas of planetary formation. Most rocky planets, like Earth, form from silicon and oxygen-rich materials. But this world is a carbon aristocrat, born in a star system with far more carbon than ours. It's a reminder that the universe crafts planets in flavors we're only beginning to catalogue, some scorching hot, others icy, and a few, like this one, literally priceless. Yet for all its allure, 55 Cancri E has a dark side literally. Tidally locked to its star, one hemisphere forever faces the inferno while the other languishes in eternal night. The day side might glow like a cosmic jewel, but the night side, a frozen wasteland where carbon could form strange, unknown allotropes under the extreme cold and pressure. This diamond planet isn't just a celestial oddity, it's a window into how extreme environments rewrite the rules of chemistry. Under those conditions, carbon doesn't just become diamond. It might morph into exotic forms we've never seen, like hexagonal diamonds or even metallic carbon. Every flicker of light we detect from this distant world carries secrets about how elements behave when pushed to their limits. So while we'll never carve jewelry from its crust, 55 Cancri E offers something far more valuable, a masterclass in the universe's boundless creativity. That breathtaking Hubble image of the pillars of creation, the towering tendrils of gas and dust in the Eagle Nebula, might already be a cosmic ghost. The photograph, taken in 1995, reveals these majestic structures stretching 4 light-years high, where newborn stars flicker to life like distant fireflies. But here's the unsettling truth. We're looking at a celestial illusion, a snapshot frozen in time from 7,000 years ago, the distance light had to travel to reach us. And by now, a nearby supernova's shockwave could have already blasted through those fragile columns like a tidal wave through sandcastles. We won't know for sure for another 1,000 years. That's how long it'll take light from the nebula's current state to finally reach Earth. Think about it, we're staring at a postcard from the past while the real thing may have already crumbled. The evidence, subtle clues in the original image. Infrared observations reveal scorching hot gas around the pillars, hinting at a supernova's aftermath. And in 2007, Spitzer Space Telescope detected a telltale bubble of expanding material nearby, likely the shockwave's leading edge. By the time Hubble revisited the pillars in 2014, the new images showed eerie changes, gaseous wisps evaporating faster than expected, as if something violent had already disturbed them. Yet even if the pillars are gone, their legacy isn't. The same shockwave that might have shattered them also sent compressed waves of matter barreling through space, triggering new star formation elsewhere in the nebula. Destruction and creation locked in an endless dance. Those towering columns taught us how stars are born, their delicate balance of gravity and radiation sculpting cosmic nurseries. Now they might teach us how stellar explosions reshape entire galaxies. Here's the bittersweet twist: every time we gaze at the night sky, we're time travelers. The Andromeda Galaxy, a snapshot from 2.5 million years ago. The Orion Nebula, a memory from 1,300 years past. Even our own sun's light takes 8 minutes to reach us, meaning if it vanished right now, we'd bask in its glow for 8 more minutes, blissfully unaware. The universe doesn't just hide its secrets across space, but across time itself. So while we wait for light to deliver the pillar's fate, we're left with a haunting reminder. Beauty in the cosmos is often fleeting, and sometimes the most iconic sights are already gone before we even get to say goodbye. Here's something you won't find on any Earth-based growth chart. Astronauts come back from space measurably taller, sometimes by as much as 5 centimeters. That's right, floating in microgravity doesn't just give you a break from gravity's constant tug. It literally stretches you out. Without the force that normally compresses your spine, the fluid-filled discs between your vertebrae expand like coiled springs finally allowed to relax. Imagine your spine, after a lifetime of being gently squished, suddenly getting the chance to stretch to its full, unhindered length. The result, space crews temporarily gain the kind of height boost most of us only dream of in adolescence. But this cosmic growth spurt isn't all good news. That extra height comes with a price often paid in back pain. Without gravity's constant pressure, the muscles supporting the spine weaken, and the ligaments that normally stabilize everything loosen up. When astronauts return to Earth, gravity reasserts its dominance, crushing those expanded discs back down. The sudden compression can feel like wearing an invisible weight vest, leaving many crew members hunched and sore for weeks. Some even report shooting pains down their legs as nerves, adjusted to their new space-long alignment, get abruptly pinched. It's a stark reminder that our bodies evolved for Earth's relentless pull, not the weightless freedom of orbit. The strangest part, this isn't just a temporary quirk. Studies of long-duration astronauts show their spines don't always return to their original length. After months in space, some lose the natural curve in their lower backs, leaving them with flatter, stiffer spines, almost like the body forgets how to arrange itself under gravity's rules. Scientists are still untangling the long-term effects, but one thing's clear: space doesn't just change how we move, it reshapes us right down to our skeletons. Think about that next time you stand up straight. Your posture isn't just habit, it's a negotiation with an invisible force that's been molding life for billions of years. And for astronauts, that negotiation gets put on pause, revealing just how deeply gravity writes the script for our bodies. So while floating might sound like a dream, the reality is a little more complicated. You might leave Earth one height and come back another, but your spine will remember the cost. Rising from the rust-colored plains of Mars like a titan frozen in time, Olympus Mons isn't just the tallest volcano in the solar system, it's a staggering monument to planetary extremes. This shield volcano towers 22 kilometers above the surrounding terrain, making Mount Everest look like a mere foothill at less than a third of its height. But raw altitude isn't even the most mind-bending part. Olympus Mons sprawls across an area roughly the size of Arizona, its base stretching 600 kilometers wide, so vast that standing on its lower slopes you wouldn't even see the summit. The curvature of Mars itself would hide it beyond the horizon. What created such a colossal landform? The secret lies in Mars' missing plate tectonics. Unlike Earth, where shifting crustal plates move over hot spots creating chains of volcanoes like Hawaii's islands, Mars' crust remains static. Here, a single volcanic hotspot could erupt continuously for billions of years, piling lava flow upon lava flow into a single, monstrous peak. With no tectonic movement to drift the volcano away from its magma source, Olympus Mons grew unchecked, its slopes building at a gentle 5-degree angle shallow enough that climbing it would feel more like hiking an endless incline than scaling a cliff face. And those slopes tell another story. The volcano's flanks are scarred by lava channels and collapsed pits, evidence of ancient eruptions where molten rock raced downhill for hundreds of kilometers. Some lava tubes might still be intact today, their ceilings holding up under Mars' weaker gravity, potential shelters for future astronauts against radiation and dust storms. The scale becomes even more surreal when you realize Olympus Mons isn't alone. It's part of the Tharsis Montes trio, a family of neighboring giants that together form a bulge covering nearly 25% of Mars' surface. This region's sheer weight may have actually tilted the entire planet's axis long ago, reshaping its climate in the process. Yet for all its grandeur, Olympus Mons is likely dormant now, its last eruptions occurring perhaps a few million years ago, a blink in geologic time. Future explorers might one day hike its caldera, a depression 80 kilometers wide where lava lakes once bubbled. From that vantage point, the horizon would curve visibly beneath their feet, the thin Martian atmosphere stretching into darkness above an ancient battlefield of fire and rock. This isn't just a record-breaking mountain, it's a testament to how planetary quirks can amplify geologic forces beyond earthly imagination. Where our world spreads volcanic activity across thousands of vents, Mars concentrated its fury into a handful of giants, creating landmarks that redefine what a volcano can be. Olympus Mons doesn't just overshadow Earth's peaks, it shatters our very notion of how mountains are born. While most planets spin like tops as they orbit the Sun, Uranus performs a cosmic barrel roll, rotating almost perfectly on its side with an astonishing 98-degree tilt. Picture a bowling ball knocked sideways mid-roll, forever spinning with its poles nearly level with its orbit. This bizarre orientation means Uranus seasons aren't just extreme, they're downright surreal. For 21 Earth years straight, one pole basks in uninterrupted sunlight while the other plunges into frigid darkness. Then, as the planet completes its 84-year orbit, the roles reverse. Imagine living in a world where summer means 42 straight years of daylight, followed by 4 decades of winter night so deep it would make Arctic winters look like brief sunsets. What could have knocked a planet so massive onto its side? The leading theory involves a cataclysmic collision, one so violent it reshaped Uranus' entire destiny. Early in the solar system's chaos, an Earth-sized protoplanet may have slammed into Uranus with enough force to topple its rotation. The impact wouldn't just have tilted the planet, it could have also vaporized primordial oceans, scattered debris into orbit, and left Uranus with an unnaturally cold core compared to other gas giants. That collision might even explain why Uranus radiates so little heat, as if the impact blasted away its internal energy like a punch to the cosmic gut. But the tilt isn't just a curiosity, it rewrites the planet's weather. Without the steady day-night cycle we're used to, Uranus' atmosphere churns in ways that baffle scientists. When Voyager 2 flew by in 1986, its cameras captured a nearly featureless blue-green orb, earning Uranus the nickname the most boring planet. But modern telescopes reveal a different story. Near the poles, where sunlight lingers or vanishes for decades, storms erupt with winds exceeding 900 kilometers per hour. Methane clouds whip around like smoke rings, and the upper atmosphere mysteriously warms during solstices, defying all expectations. Here's where it gets weirder. Uranus' magnetic field is just as off-kilter as its rotation. Unlike Earth's relatively tidy north-south magnetosphere, Uranus' magnetic poles emerge near its equator, tilted 60 degrees from its already sideways axis. This creates a magnetic field that wobbles like a drunk compass needle, opening and closing as the planet rolls along its orbit. Solar wind particles might surf these chaotic field lines, sparking auroras that spiral around the planet in unpredictable patterns. Light shows no Earth-bound observer could ever anticipate. Yet for all its oddities, Uranus holds clues to one of astronomy's biggest mysteries, the prevalence of exoplanets with similar tilts. Out there in the cosmos, sideways worlds might be common, and studying Uranus gives us a template for how such planets behave. Its bizarre seasons test the limits of atmospheric modeling. Its lopsided magnetism challenges theories of planetary interiors, and its violent origin story reminds us how chaotic young solar systems can be. So next time you hear someone call Uranus boring, set them straight literally. This isn't just a planet spinning oddly. It's a cosmic accident frozen in time, a laboratory for extreme seasons, and a warning that even in the orderly dance of the solar system, chaos leaves its mark. One colossal impact billions of years ago didn't just tilt a world, it created a perpetual astronomical marvel, rolling through space like a rebellious child refusing to follow the rules. The moon isn't the silent, dead world it appears to be beneath its cratered surface. It trembles with quakes that would feel right at home on Earth. These aren't echoes of some long-lost geologic activity. They're moonquakes, and the Apollo astronauts left behind seismometers to prove it. Between 1969 and 1977, those instruments recorded over 12,000 seismic events, painting a picture of a moon far more dynamic than we ever imagined. Some were shallow, triggered by meteorites slamming into the surface or the brutal temperature swings between lunar day and night, cracking the crust like an ice cube dropped in boiling water. Others ran deeper, much deeper, with vibrations lasting upward of 10 minutes, as if the entire moon were ringing like a bell. But the strangest quakes came from somewhere in between. Tidal moonquakes caused by Earth's gravitational pull ripple through the lunar subsurface every 27 days like clockwork, timed perfectly with our planet's tug. The moon's crust stretches and compresses, groaning under forces that would barely register on Earth. Even weirder are the deep moonquakes, originating 700 kilometers below the surface, far deeper than any quake on our planet. These weren't random, they followed predictable paths, flaring up in the same narrow zones month after month. Yet despite decades of study, no one's entirely sure what's causing them. One theory points to molten remnants of the moon's ancient magma ocean, cooling and cracking as they solidify. Others suspect tidal stresses aren't just flexing the crust, they're squeezing pockets of partially melted rock deep within the mantle, forcing them to shift unpredictably. Then there's the wild card, tidal forces from the sun, which might be adding extra strain to an already fragile interior. Whatever the cause, these quakes reveal a moon that's still geologically alive, its interior whispering secrets we're only beginning to decode. And here's what keeps scientists up at night. Some of those quakes were strong, really strong. The most powerful registered up to 5.5 on the Richter scale, enough to topple furniture and crack walls if they happened in a city. For future lunar bases, that's more than a curiosity, it's a potential hazard. Imagine setting up a habitat only to have the ground suddenly lurch beneath you, sending equipment flying and fissures snaking across the regolith. The moon doesn't have tectonic plates like Earth, but it doesn't need them to pack a punch. What's truly fascinating is how differently these quakes behave. On Earth, quakes fade quickly as energy dissipates through our planet's watery crust and molten layers. But the moon's dry, rigid interior lets vibrations linger, turning every quake into a drawn-out echo. Some recordings show waves bouncing back and forth for hours, as if the moon can't quite let go of the energy. It's a reminder that even our closest celestial neighbor plays by its own rules, rules we're still struggling to understand. So the next time you look up at that serene, gray face in the sky, remember, it's not just a frozen relic, it's a world with a pulse, shuddering under forces both familiar and utterly alien. Those quakes aren't just curiosities, they're clues, hinting at a hidden lunar history we've barely begun to unravel. Far beyond our solar system, in the depths of space, floats a cloud of water vapor so massive it defies comprehension, 140 trillion times the volume of all Earth's oceans combined. This isn't some scattered mist drifting between stars. It's a colossal reservoir wrapped around APM 08279 plus 5255, a blazing quasar 12 billion light-years away, shining with the fury of 1,000 galaxies. Picture a single cosmic storm cloud swirling around an unfathomable energy source, holding enough water to drown every desert, fill every lake, and still leave enough to flood the solar system 1,000 times over. What makes this discovery so staggering isn't just the scale, it's the paradox. Quasars are among the most violent objects in the universe, powered by supermassive black holes devouring matter so fast they outshine entire galaxies. The environment around APM 08279 plus 5255 is a maelstrom of radiation, gravitational forces, and temperatures that would vaporize steel. Yet somehow, within that chaos, water survives, not as ice or liquid, but as a vast shroud of superheated steam, stretching hundreds of light-years across. How does water exist in such an inferno? The answer lies in the cloud's sheer size. While the quasar's core burns at millions of degrees, the outer reaches of this vapor cloud are just cold enough, around -53 degrees Celsius, for water molecules to cling together. It's a delicate balance, like a snowflake surviving inches from a bonfire. But here's the real kicker. This isn't just any water. Spectroscopic readings reveal it's the same H2O we drink, bathe in, and depend on for life. The only difference, there's enough of it here to fill an ocean on every planet in the Milky Way with plenty to spare. Scientists suspect this reservoir didn't form by chance. Quasars like APM 08279 plus 5255 act as cosmic factories, forging heavy elements and complex molecules in their turbulent wakes. The water was likely crafted from hydrogen and oxygen atoms blasted into space by dying stars, then swept up by the quasar's gravitational pull. Over billions of years, radiation fused them into molecules, creating this unimaginable oasis in the void. But here's what truly boggles the mind. We're seeing this quasar as it existed 12 billion years ago, when the universe was barely a toddler. Back then, water shouldn't have been this abundant. Yet there it is, proof that the ingredients for life existed far earlier and in far greater quantities than anyone predicted. If water could thrive in the most hostile corners of the young cosmos, might it also have seeded planets back when Earth was still molten rock? This discovery shatters our assumptions about where and when water can exist. We used to think of it as a rare luxury in space, confined to icy comets or hidden beneath alien moons. But APM 08279 plus 5255 proves water isn't just scattered. It's woven into the fabric of the universe, pooling in places we never thought to look. And while this particular reservoir is far too violent to harbor life, its existence hints at countless others waiting in quieter corners of the cosmos. So the next time you take a sip of water, remember, you're tasting a substance so universal, it floats in clouds larger than galaxies. The same molecules that quench your thirst are out there right now, swirling around black holes, drifting between stars, and maybe, just maybe, filling oceans on worlds we've yet to discover. The universe isn't just vast, it's drenched. Saturn isn't just the solar system's crown jewel, it's also the only planet light enough to float. That's right, if you could find a bathtub big enough, Saturn would bob like a cosmic rubber duck. The secret lies in its density, a mere 0.687 grams per cubic centimeter, less than water's 1 gram per cubic centimeter. To put that in perspective, Earth's rocky bulk gives it a density 5.5 times higher, making our planet sink like a stone. But Saturn, it's essentially a gigantic, swirling ball of hydrogen and helium, so loosely packed that it defies everything we know about planetary heft. Imagine constructing a cosmic swimming pool vast enough to test this theory. Saturn's diameter stretches over 116,000 kilometers, 9 times wider than Earth. You'd need an ocean dwarfing even the Sun to submerge it, with water volumes measured in sextillions of gallons. Now picture the ringed giant gently lowered in, its pastel bands rippling as it displaces an unfathomable mass of liquid. Despite weighing 95 times more than Earth, Saturn's sheer size spreads that mass so thin it would float with about 30% of its bulk above the surface, like an iceberg in slow motion. But here's the catch. This thought experiment reveals more than just a quirky planetary fact. Saturn's buoyancy hints at its origins. Unlike rocky worlds forged in fire and collision, gas giants like Saturn formed in the outer solar system's freezing reaches, where lighter elements like hydrogen could accumulate without being blown away by the young sun's heat. Over eons, gravity sculpted these gases into a sphere so vast yet so insubstantial that its core, if it even has a distinct one, remains shrouded in layers of metallic hydrogen deeper than Earth's entire diameter. The floating illusion wouldn't last long, though. Saturn's composition means any hypothetical water contact would trigger catastrophe. The planet's upper atmosphere is mostly hydrogen, a gas so reactive it would bond explosively with oxygen in the water, igniting storms of literal firestorms atop the waves. And those iconic rings, they're made of ice and rock, so they'd likely detach and dissolve like sugar in tea, leaving Saturn bald and bobbing awkwardly in its makeshift cosmic bathtub. This isn't just a fun hypothetical, it's a lesson in celestial diversity. Saturn's buoyancy proves that planets aren't defined by weight alone. A world can be unimaginably massive yet lighter than the lightest substance on Earth, its very existence challenging our assumptions about what makes a planet solid or substantial. Next time you see Saturn through a telescope, remember, you're looking at a cosmic anomaly, a titan that floats not on water, but on the delicate balance of gravity and gas. The coldest place in the known universe isn't drifting in some distant void, it's floating right above our heads aboard the International Space Station. NASA's Cold Atom Lab has created temperatures just a hair above absolute zero, plunging to negative 273.15 degrees Celsius. To grasp how mind-numbingly cold that is, consider this. Even the Boomerang Nebula, long considered the universe's natural deep freeze at negative 272 degrees, is practically balmy by comparison. The difference might seem slight, but in the quantum world, it's the gap between stillness and chaos. What makes the Cold Atom Lab so special? It's all about eliminating movement. At normal temperatures, atoms zip around like hyperactive kids, but here, lasers and magnetic fields slow them to a crawl. We're talking speeds slower than a crawling baby, just centimeters per second. Then, as a final coup de grace, the lab removes nearly all energy, leaving atoms hovering in a state of near-perfect motionlessness. In this frigid realm, atoms stop behaving like particles and start acting like waves, overlapping in ghostly quantum states that defy common sense. Now compare that to the Boomerang Nebula. Located 5,000 light-years away, this cosmic icebox owes its chill to a dying star flinging gas outward at 500,000 kilometers per hour. The rapid expansion cools the gas, much like how spraying deodorant feels cold on your skin. But here's the irony. While the nebula's vast expanse makes it the coldest natural spot we've found, it can't compete with humanity's tiny, intentional deep freeze in space. The real magic happens in the lab's microgravity environment. On Earth, gravity would yank these ultra-cold atoms downward, ruining the experiment. But in orbit, researchers can hold atoms in place for minutes rather than seconds, unlocking new ways to study quantum mechanics. Imagine peering into the fabric of reality itself, where the usual rules break down and particles exist in multiple places at once. These experiments might one day revolutionize technology, from ultra-precise navigation systems to quantum computers solving problems today's machines wouldn't touch in a billion years. So why does any of this matter? Because extremes reveal truths. By pushing temperatures to the brink, we're glimpsing the universe's underlying symphony, one usually drowned out by the noise of heat and motion. Whether it's the unnatural chill of the Cold Atom Lab or the Boomerang Nebula's natural frost, both remind us, cold isn't just emptiness. It's a window into how the cosmos works at its most fundamental level, where particles dance to quantum tunes we're only beginning to hear. Tucked away in the heart of the Milky Way, near the constellation Sagittarius, floats a cosmic cocktail so vast it could serve every person on Earth a drink forever. Sagittarius B2, a sprawling molecular cloud 463 billion kilometers wide, contains enough ethanol to fill 400 trillion pints of beer. That's not just a few stray molecules, we're talking about billions of liters of alcohol drifting through the void, mingling with clouds of formaldehyde and other organic compounds. If you could somehow bottle it, every human alive could drink 1,000 pints an hour for 1 billion years and still not drain this interstellar distillery. But before you imagine floating through space with a straw, here's the sobering truth. Sagittarius B2 isn't exactly a party spot. The cloud's ethanol isn't swimming in some celestial martini glass. It's dispersed at a density so thin, you'd need to scoop up a volume of space larger than the solar system just to get a single sip. And even if you could gather enough, the mix includes toxic cousins like vinyl alcohol and methanol, ingredients better suited for fueling rockets than fueling a good time. That said, the sheer presence of such complex molecules raises a tantalizing question. If alcohol forms naturally in the chaos of space, what other life-building compounds might be floating out there? The origins of this cloud are as fascinating as its contents. Sagittarius B2 sits near the Milky Way center, a region crammed with newborn stars and the remnants of stellar explosions. Radiation from these stars strips electrons from atoms, triggering chemical reactions that build increasingly complex molecules. Ethanol forms when carbon, hydrogen, and oxygen atoms plentiful in these stellar nurseries collide and bond under the right conditions. Over millennia, these reactions snowball, creating vast reservoirs of organic material that could one day seed planets with the ingredients for life. What's truly wild is that this isn't even the only boozy cloud in the galaxy. Astronomers have spotted clouds of methanol near the star-forming region W3OH, and even sugar molecules floating in the gas around a young sun-like star. The universe, it seems, has a knack for brewing up the building blocks of chemistry in the most unexpected places. So while you won't be booking a trip to Sagittarius B2 for happy hour anytime soon, its existence offers a dizzying perspective on how chemistry works on a galactic scale. The same processes that mix cocktails in space might have once delivered the raw materials for life to Earth, fermented gifts from the cosmos, raining down on our planet billions of years ago. Next time you raise a glass, consider this. Somewhere out there, the universe is doing the same, on a scale so grand, it makes the world's biggest brewery look like a lemonade stand. Cheers to that. Earth doesn't always dance solo in space. Sometimes it picks up a cosmic hitchhiker. Meet 2006 RH-120, a car-sized asteroid that temporarily became Earth's second moon in 2006, circling our planet for 18 months before drifting back into the solar system's embrace. These fleeting companions, dubbed minimoons, aren't permanent fixtures like our familiar lunar neighbor. They're asteroid strays snagged by Earth's gravity during close encounters, forced into chaotic orbits that last anywhere from a few months to several years before the sun's pull wins them back. What makes these celestial tagalongs so fascinating is their unpredictability. Unlike the moon's stately procession, minimoons like 2006 RH-120 follow wild, lopsided paths, looping around Earth in spirals or figure eights that resemble a drunkard stumble. Their orbits aren't neat circles but elongated ellipses, stretched so thin that at their farthest point they might be 3 times the moon's distance, only to swoop back in closer than some satellites. This erratic behavior comes from their tenuous grip on being moons at all. With gravity's tug-of-war between Earth and the Sun constantly shifting, these rocks exist in a precarious balancing act, never sure which force will claim them next. The real surprise, these temporary moons are more common than we thought. Before 2006 RH-120, astronomers assumed such captures were rare, maybe once-a-century events. But improved telescopes have revealed a different story. In 2020, scientists spotted another minimoon, 2020 CD3, a washing machine-sized rock that orbited Earth for nearly 3 years before breaking free. Current estimates suggest at least one minimoon is circling Earth at any given time, most too small or dark to detect with current technology. Here's where it gets even stranger. Some minimoons might not be asteroids at all. Simulations suggest a fraction could be human-made space junk from old missions, discarded rocket boosters, or lunar ejecta drifting for decades before Earth recaptures them. Imagine the cosmic irony, a relic from the Apollo era, mistaken for a natural satellite, quietly returning to haunt the skies it once departed. Yet for all their transience, minimoons offer tantalizing opportunities. Their weak gravity and close proximity make them ideal practice targets for future asteroid missions, cheaper to reach than main belt asteroids, but just as scientifically valuable. Some proposals even suggest harvesting them for resources, turning these cosmic way stations into stepping stones for deeper space exploration. But perhaps their greatest lesson is humility. For centuries, we've taken the moon's presence for granted, as if Earth's celestial companionship were a singular privilege. Minimoons remind us that our planet's gravitational embrace is wide enough to occasionally shelter other wanderers, briefly sharing the stage with our ancient lunar partner before the universe calls them elsewhere. So the next time you gaze at the moon, remember, somewhere out there, Earth might already be hosting another guest, spinning silently in the shadows, waiting for its moment to slip away unnoticed. Every second, the sun unleashes enough energy to power human civilization for nearly 700,000 years, a staggering 380 yottawatts. To put that into perspective, 1 yottawatt is a 1 followed by 24 zeros. That's a number so vast, it dwarfs every power plant, every battery, every drop of oil humanity has ever consumed combined. Imagine tapping into just 1 second of the sun's output. You could light up every city, charge every device, and fuel every car on Earth for centuries without needing another spark. But here's the catch: we're barely scratching the surface of what's possible. Right now, all the solar panels, wind turbines, and nuclear reactors on Earth harness less than 1/5000th of the energy the sun showers on our planet every day. The rest radiates back into space, an unimaginable feast of power slipping through our fingers. Even the most advanced solar farms only convert a fraction of sunlight into usable electricity. It's like standing under a waterfall with a thimble, catching a few drops while an ocean rushes past. What if we could capture just a fraction more? Consider this: a single hour of sunlight holds more energy than humanity uses in a year. If we could efficiently collect and store even a sliver of that, fossil fuels would become obsolete overnight. No more oil spills, no more coal emissions, just clean, limitless power drawn straight from the cosmos. The technology isn't science fiction either. Space-based solar farms orbiting collectors beaming energy back to Earth are already in development. These wouldn't just work in daylight, they'd operate around the clock, unfiltered by clouds or atmosphere, turning sunlight into a constant global power source. The numbers get even wilder when you scale up. The sun's total output over its lifetime will exceed the energy stored in all the coal, gas, and uranium deposits on Earth by a factor of billions. Yet here's the cosmic irony: despite floating in an ocean of energy, we're still burning ancient plants and splitting atoms to keep the lights on. The solution isn't just engineering, it's imagination. The sun doesn't just light our days, it's a blueprint for survival, proving that the universe provides far more than we've learned to take. So next time you feel sunlight on your skin, remember, you're being brushed by a force that could rewrite human destiny. The challenge isn't whether the energy exists, it's whether we're bold enough to reach for it. After all, the sun isn't just a star. It's the ultimate power plant burning silently in the sky, waiting for us to catch up. Deep in the heart of the Perseus galaxy cluster, 250 million light-years from Earth, a supermassive black hole isn't just lurking, it's singing. Thanks to NASA's Chandra X-ray Observatory, we've captured this cosmic bass note, a sound wave rippling through intergalactic gas that translates to a B-flat 57 octaves below middle C. To grasp how deep that is, imagine the lowest pipe on a cathedral organ, then descend further into frequencies so profound, no human ear could ever detect them. This isn't just background noise, it's the vibration of a black hole reshaping its universe, a single note sustained for over 2 billion years. How does a vacuum of darkness produce sound? The secret lies in the superheated gas swirling around the black hole's event horizon. As material spirals inward, it churns the surrounding plasma, creating pressure waves that pulse outward like ripples in a pond. These waves compress and heat the galaxy cluster's gas, preventing it from cooling and collapsing into new stars, effectively hitting pause on galactic evolution. The result, a cosmic feedback loop where the black hole's voice controls the growth of its own galaxy. Here's where it gets haunting. The note itself is impossible to hear naturally. Its wavelength stretches across 35,000 light-years, requiring scientists to transpose it upward by 57 octaves just to make it audible to human ears. The original frequency pulses once every 10 million years, a tempo so glacial it defies musical convention. Yet when sped up, it echoes like the groan of a distant giant, a sound so eerie it could score a horror film about the universe itself. What's truly revolutionary about this discovery isn't just the novelty of a singing black hole. These sound waves carry energy enough to keep entire galaxy clusters simmering at millions of degrees. Without them, the Perseus cluster's gas would have cooled eons ago, birthing countless new stars and altering the galactic landscape beyond recognition. Instead, the black hole's drone acts as a cosmic thermostat, maintaining equilibrium on a scale so vast it redefines our understanding of how structures evolve in space. But don't expect a celestial symphony. This is a solo performance, one sustained note echoing across eternity, so low it vibrates the fabric of space-time itself. Next time you press play on your favorite song, consider this. The universe has been composing its own melodies for billions of years. We're just beginning to listen. Standing on a beach, letting sand trickle through your fingers, it's easy to feel overwhelmed by the sheer number of grains, each one tiny, yet collectively countless. Now imagine this: every speck of sand on every beach, every desert dune, every ocean floor across Earth amounts to roughly 7.5 quintillion grains. That's a number so large, writing it out would take 19 digits. But here's the mind-blowing twist: the universe holds more stars than all those grains combined. Not just a few extra hundreds of times more. Forget counting stars in our Milky Way. We're talking about the entire observable cosmos, where estimates suggest there are over 100 billion galaxies, each brimming with hundreds of billions of stars. Let's break that down. If our galaxy alone contains around 100 billion stars, give or take a few tens of billions, multiply that by the estimated number of galaxies, and you're looking at a figure so vast it defies human intuition. 10 sextillion stars, 100. The math gets fuzzy at these scales, but one thing's certain. Even if every grain of sand on Earth represented 1,000 stars, we'd still run out of sand long before we ran out of cosmic lights. This isn't just about big numbers, it's about perspective. Those grains of sand took hundreds of millions of years to form, weathered from mountains, swept by rivers, and polished by waves. Yet the stars above tell an even grander story. Each one is a nuclear furnace, some birthing planets, others collapsing into black holes, all woven into a tapestry stretching back 13.8 billion years. And here's the kicker: we're only counting the observable universe, the fraction within our cosmological horizon. Beyond that, the cosmos might stretch infinitely, making our sand grain comparison seem quaint. Picture this: if every star were a single pixel on your screen, you'd need a display the size of a city to capture them all. And that's just the stars, not the planets, nebulae, or black holes orbiting them. The scale tips into the absurd when you consider that some stars, like red supergiants, could swallow our solar system whole, yet they're still outnumbered by grains of sand in this thought experiment. What does this mean for us? For starters, it humbles the idea that we're alone. With so many stars, the odds of other Earth-like worlds skyrocket, but it also underscores how much we don't know. We've catalogued a fraction of a percent of the stars in our galaxy, let alone the universe. Every telescope pointed skyward isn't just counting, it's sifting through cosmic haystacks for needles that might rewrite biology, physics, even philosophy. The next time you're on a beach, scoop up a handful of sand. Each grain is a monument to Earth's patience. Now look up. Those pinpricks of light, they're the universe's reply, a whisper across the void that says, you haven't even begun to see what's out there. When Pluto was discovered in 1930, it hadn't even completed a third of its journey around the Sun, and nearly a century later, it still hasn't finished a single orbit. That's because a year on this distant dwarf planet lasts a staggering 248 Earth years, making its journey around the Sun the longest of any recognized world in our solar system. To put that in perspective, if you'd celebrated your first birthday the day Pluto was discovered, you'd be turning 94 by the time it finally completed its first observed year in 278. Pluto's glacial pace isn't just a quirk, it's a consequence of its peculiar, stretched-out orbit. While Earth cruises along a nearly circular path, Pluto's trajectory is more like a lopsided oval, swinging from 30 times the Sun-Earth distance at its closest to almost 50 times that distance at its farthest. At those extremes, sunlight is so feeble it would barely register as twilight to our eyes, and temperatures plunge to negative 230 degrees Celsius, cold enough to freeze nitrogen solid. Here's what's wild. Since its discovery, Pluto has actually moved closer to the Sun, reaching its nearest point in 1989 before beginning its long trek back into the deep freeze. Imagine a world where summers last decades, where a single season spans generations. By the time Pluto completes its next orbit in the 23rd century, human civilization might have colonized Mars, harnessed fusion energy, or even made contact with alien life, all within what amounts to one Plutonian year. What's even stranger is how Pluto's elongated orbit interacts with Neptune. For 20 years out of every orbit, including the period between 1979 and 1999, Pluto actually dips inside Neptune's path, making it technically closer to the Sun than its giant neighbor. Yet the two will never collide. Their orbits are locked in a gravitational resonance, ensuring they'll never get too close, like dancers circling each other in perfect rhythm. This extreme orbit also means Pluto's seasons are unlike anything in the inner solar system. As it inches away from the Sun, its thin atmosphere, mostly nitrogen with traces of methane and carbon monoxide, begins a slow-motion collapse, freezing out and snowing onto the surface. By the time it reaches its most distant point, Pluto's sky will have vanished entirely, leaving its frozen plains in perpetual darkness. But here's the kicker: we've never seen a full Plutonian year. Even our best images from New Horizons in 2015 captured just a sliver of its seasonal cycle. By the time it completes its first observed orbit, our distant descendant might look back at those grainy black and white photos from 1930 and marvel at how little we knew about this enigmatic world and how much it's taught us since. Pluto's marathon year isn't just a curiosity. It's a reminder that time moves differently in the outer solar system, where the universe operates on a timescale even grander than human history. Deep in the heart of our galaxy, the Milky Way hides a flavor that would seem right at home in your breakfast smoothie: raspberries. Thanks to the IRAM telescope's discovery near the colossal gas cloud Sagittarius B2, astronomers detected vast amounts of ethyl formate, the very same molecule responsible for giving raspberries their sweet, fruity aroma. Picture this: drifting through the cosmic dust lanes of our galaxy are enough organic compounds to flavor an interstellar dessert, except instead of a kitchen, this molecular cocktail was stirred together in the violent birthplaces of stars. What's fascinating isn't just the presence of this compound, it's the sheer volume. Sagittarius B2, a sprawling stellar nursery near the galactic center, is a veritable factory of complex molecules. Amidst the chaos of newborn stars and shockwaves from supernova, atoms collide and bond in ways that mimic earthly chemistry. Ethyl formate forms when ethanol and formic acid, both abundant in space, meet under the right conditions. The result, a molecular cloud that, if you could take a sniff and survive the vacuum and radiation, would smell eerily like a bowl of fresh berries mixed with a splash of rum, another flavor ethyl formate helps create. Here's the kicker: this discovery doesn't just hint at a quirky cosmic coincidence. It's part of a growing list of organic molecules found in space, from sugars like glycolaldehyde to amino acids. These building blocks scattered across the galaxy suggest that the raw ingredients for life aren't rare, they're practically everywhere. Sagittarius B2 alone contains enough complex chemistry to stock 1 million interstellar grocery stores, proving that the universe has a knack for cooking up the same compounds we associate with life, even in the most inhospitable places. Now, before you imagine the Milky Way as some giant cosmic smoothie, remember, space isn't a kitchen. The ethyl formate in Sagittarius B2 is incredibly diffuse, so spread out that you'd need to gather a volume of space larger than our solar system to collect a single whiff. And it's mixed with far less appetizing molecules like hydrogen cyanide and sulfur compounds, but that doesn't make the discovery any less astonishing. The fact that these molecules exist at all, floating in the void, tells us something profound about chemistry's universality. The same reactions that flavor your jam might also flavor the birthplaces of stars. So next time you bite into a raspberry, consider this. Somewhere out there, the galaxy is brewing its own version, not in a jar, but in the vast, invisible clouds that stretch between the stars. It's a reminder that the universe doesn't just astonish us with its scale. It connects with us in the smallest, most familiar ways, turning something as simple as a fruit scent into a cosmic signpost pointing toward the chemistry that binds us all. Floating in microgravity might seem like a dream for weary muscles, but for an astronaut's heart, it's a recipe for radical transformation. Without Earth's relentless pull, this vital organ doesn't just slack off, it physically reshapes itself, evolving into a more spherical form over time. MRI scans of astronauts before and after long-duration missions reveal this startling metamorphosis. A heart that once resembled a tapered, elongated oval, gradually rounding into a shape closer to a baseball. The science behind this is as fascinating as it is unsettling. On Earth, gravity forces the heart to work harder, pumping blood upward against the constant downward tug. In space, that challenge vanishes. Blood redistributes evenly, easing the heart's workload and causing it to lose muscle mass, a condition called cardiac atrophy. Think of it like a runner who stops training. Within weeks, their endurance fades. For astronauts, 6 months in orbit can reduce heart mass by nearly 10%, a change equivalent to years of aging. But here's where it gets even more intriguing. This spherical shift isn't just about laziness, it's an adaptation. A rounder heart pumps blood more efficiently in weightlessness where fluids aren't pulled downward. The problem, returning to Earth's gravity, becomes a shock to the system. Imagine a balloon stretched vertically suddenly forced back into a squat shape. Astronauts often struggle with dizziness and blood pressure drops upon re-entry, their reshaped hearts temporarily struggling to readjust to fighting gravity again. The implications stretch far beyond spaceflight. Studying these changes helps scientists understand heart conditions like atrophy in sedentary patients or the elderly, offering clues to combat muscle loss on Earth. Some researchers even suggest that astronauts' hearts mimic aspects of heart failure, providing a unique model to test treatments. Yet the biggest mystery remains: what happens during years-long missions like a trip to Mars? Current exercise regimens on the ISS 2 hours of daily cardio and resistance training only partially offset the effects. Without new countermeasures, explorers might arrive on the red planet with hearts too weakened for strenuous activity. So the next time you feel your pulse after climbing stairs, thank gravity. It's not just keeping you grounded, it's keeping your heart in fighting shape. For astronauts, that constant tug is a lifeline they temporarily leave behind, returning with hearts that tell a story of adaptation, challenge, and the profound ways space rewrites even our most vital organs. Stretching across 10 billion light-years of space, an almost inconceivable ribbon of galaxies, gas, and dark matter, the Hercules Corona Borealis Great Wall isn't just a structure. It's the universe's largest known architectural marvel, so vast it defies the very laws we thought governed cosmic organization. Picture this, a spiderweb woven on a scale where each strand is a galaxy cluster, and the entire web is so enormous that light, racing at 300,000 kilometers per second, would take 10 billion years to traverse it. If our Milky Way were a single grain of sand, this wall would stretch from New York to Los Angeles over and over again, millions of times. What makes this cosmic behemoth even more mind-bending is how it challenges our understanding of the universe's limits. According to the principle of cosmology, matter should be evenly distributed at the largest scales, no clumps, no gaps. Yet here's Hercules' corona borealis, a filament of galaxies so colossal it shouldn't exist. Astronomers first spotted it in 2013 while mapping gamma-ray bursts, the death cries of massive stars. These bursts acted like cosmic breadcrumbs, tracing a pattern that revealed a structure wider than anything ever seen before, roughly 1/10 the diameter of the entire observable universe. Zoom in, and the wall's anatomy gets even stranger. It's not a solid barrier, but a labyrinth of galaxy clusters and superclusters strung together by tendrils of dark matter, the invisible glue holding the cosmos together. These filaments form highways for galaxies, with gravity funneling them into dense knots where thousands of galaxies swarm like bees around a hive. Some of these clusters are so massive they bend space-time itself, creating gravitational lenses that distort the light from objects behind them. But here's the real puzzle. Hercules' corona borealis isn't alone. It's part of a growing list of impossible megastructures, like the Sloan Great Wall and the South Pole Wall, that stretch the definition of what's cosmically plausible. Their existence hints at forces we don't yet understand, perhaps relics from the universe's infancy when quantum fluctuations etched their blueprints into the fabric of space-time. What's humbling is that we're only seeing a shadow of this structure. Because of its distance, the light reaching us today shows the wall as it existed 10 billion years ago, when the universe was barely a third of its current age. By now, it might have morphed into something even grander, or dissolved into the cosmic background, its galaxies scattered by dark energy's relentless push. This isn't just a record-breaking curiosity. The Great Wall forces us to rethink how the universe organizes itself. Is it a statistical fluke, evidence of exotic physics, or a sign that our observable universe is just a pixel in an even larger, unfathomable picture? Every time we map deeper into space, we're reminded, the cosmos doesn't just exceed our expectations, it dismantles them, one galaxy filament at a time. Space rain isn't the gentle drizzle you'd expect, it's a deadly downpour of cosmic shrapnel and superheated plasma with the power to vaporize metal. Take hypervelocity micrometeoroids for starters. These aren't your average shooting stars. Tiny as grains of sand, they streak through space at speeds topping 60,000 kilometers per hour, faster than a bullet. When one slams into a satellite or spacecraft, the impact unleashes energy akin to a grenade blast, puncturing hulls and frying electronics. The International Space Station's armor can shrug off some hits, but astronauts still listen for the ominous ping of a micrometeoroid striking, a sound that means their home in orbit just dodged a cosmic bullet. Then there's the sun's version of rain, coronal showers. Imagine a thunderstorm where the raindrops are globs of plasma hotter than lava, plunging from the sun's scorching atmosphere back to its surface. These fiery droplets form along colossal magnetic loops, arcs so vast they could bridge Earth to the moon, where plasma superheated to millions of degrees gets trapped by magnetic fields. When the plasma cools slightly, it condenses into shimmering blobs that rain downward at 200,000 kilometers per hour, each droplet large enough to swallow cities whole. Solar observatories capture this eerie ballet in ultraviolet, revealing crimson tendrils of plasma cascading like waterfalls in slow motion. What makes coronal rain so bizarre is its defiance of intuition. On Earth, rain falls away from heat sources. On the Sun, it's the opposite. Plasma, after soaring into the blistering corona, cools just enough to succumb to gravity's pull, creating a surreal feedback loop of evaporation and precipitation. But don't mistake this for a gentle process. These plasma showers release enough energy to power global grids for millennia, every droplet a miniature fusion bomb. The real danger: both types of space rain expose how vulnerable our tech and future explorers are to the cosmos whims. Micrometeoroids could turn a Mars-bound ship into Swiss cheese, while coronal rain's magnetic chaos disrupts satellites and power grids. Yet there's beauty in the brutality. These phenomena remind us that weather isn't just an earthbound concept. From diamond storms on Neptune to acid showers on Venus, the universe is a master of extreme meteorology, where even a raindrop can rewrite the rules of physics. Ever feel like there just aren't enough hours in the day? Well, for astronauts orbiting Earth, time literally moves differently, not by much, but enough to bend the rules of reality as we know them. Thanks to Einstein's theory of relativity, every second spent speeding around the planet at 27,000 kilometers per hour on the International Space Station means astronauts experience time slightly slower than we do on the ground. Over a typical 6-month mission, they age about 0.005 seconds less than the rest of us. That might sound negligible, barely a blip, but multiply it across years of space travel and the effect becomes measurable. Future Mars explorers might return home technically younger than if they'd stayed put, their bodies having traversed time as well as space. The real-world implications of this time warp aren't just philosophical. GPS satellites orbiting 12,000 miles above Earth have to account for relativity daily. Without corrections, their atomic clocks would tick 38 microseconds faster each day due to weaker gravity at that altitude, throwing off location accuracy by nearly 10 kilometers within minutes. To compensate, engineers program these satellites to run slightly slower before launch, ensuring they sync perfectly with Earth-bound clocks. It's a silent dance of precision, where even the faintest hiccup in timekeeping could derail navigation systems worldwide. This phenomenon, known as time dilation, gets even wilder when you visualize it. Picture the classic twin paradox. One sibling rockets off to space at near light speed while the other stays home. Upon return, the spacefaring twin finds their Earth-bound counterpart has aged years more. Though no astronaut has yet traveled fast enough for dramatic differences, the principle holds. Speed and gravity act as cosmic timekeepers, stretching or compressing moments based on where and how you experience them. What's mind-bending is how seamlessly relativity integrates into our lives. Every time your phone pinpoints your location, it's relying on science that accounts for spacetime's flexibility. The universe doesn't just permit these quirks, it demands them, weaving time's fluidity into the fabric of reality. So while astronauts won't return looking noticeably younger, their journeys remind us time isn't a rigid arrow. It's a river flowing at different speeds depending on how you ride its currents. And somewhere in that cosmic truth lies the key to unlocking deeper mysteries like how black holes warp time entirely, or whether one day we might harness relativity to reach the stars. From diamond planets glittering in the void to black holes humming cosmic lullabies, the universe never runs out of ways to leave us speechless. Who could forget the planet where it rains molten gems, or Saturn's perfect hexagonal storm, a geometric marvel wider than Earth? Then there's that supermassive black hole in Perseus, vibrating spacetime with a note 57 octaves below anything we can hear, its song echoing for billions of years. And let's not overlook the raspberry-scented gas clouds drifting near our galaxy's heart, or the moon's slow-motion escape from Earth's grasp. Each fact is a reminder: reality outshines even the wildest sci-fi. But here's the real kicker: this is just a glimpse. For every mystery we've uncovered, 1,000 more lurk in the shadows, waiting for the next curious mind to shine a light. So tell us, which fact left you reeling? Was it the ice hidden on Mercury's scorching surface, or the way astronauts come home taller? Drop your pick in the comments, and while you're there, hit subscribe. The cosmos has endless stories to tell, and we're just getting started. As we wrap up this cosmic journey, remember, the universe isn't a static backdrop. It's a living, breathing enigma, rewriting its rules faster than we can decode them. So keep your eyes on the skies, your mind open to wonder, and that sense of awe burning bright. Because out there, beyond the reach of streetlights and city noise, the greatest show in existence is playing on an infinite loop. All you have to do is look up. The next revelation, it's already on its way.